Okay, this is a presentation that I get to in a functional programming meeting in at the end of the past month, and where I presented transient. Let's go. Well, as you can see, my graphical design abilities are more than remarkable. So I I reduced the layout to the minimum, and that's all. So the goals for a practical programmer like me, beyond any other consideration, are reusability, maintainability of the software, and working at a language the most close to the user requirements. So it has to be high level. I want to start from the beginning with a framework of a set of libraries or facilities that allows me to talk almost the same language than the requirements, but with better structure. Um, and talking about these properties, nothing is more reusable and maintainable than two kinds of things: recipes and mathematical formulas. Why? First of all, formulas use functions that transform values from A to B, from one type to another, with certain properties of composability, and they have nice binary operators with also algebraic properties, in which we can combine two elements to generate a third with the same kind, with the same type. So we can add to a third and generate, and this way is wonderful for managing mathematics. But we don't we cannot do it at on the very top level. We cannot some widgets or distributed calls or threads. Why not? And recipes are sequence of steps without too many breaks. A recipe is not a imperative sequence. We look at recipes backwards. We stop in a certain point because we have to do something different, and we return to the recipe when we have what we need available. For example, when we are cooking, we can start from the beginning, but sometimes we have to be interrupted because we have to do something, or we need some ingredient that we don't have. But no matter that, the recipe doesn't specify that. It just specifies the high level requirements for generating what the recipe is intended to do. So it's not imperative programming. A recipe is much more flexible. And the question is, we cannot do programs with these high level structures with recipes and formulas. The problem is non-composability. The non-composability is introduced by evil things like events, callbacks, routing in web application, GUIs with a mouse and widgets and buttons, etc., blocking in operations that like file read and write, or socket listening, threading. Where we have many threads, we need some kind of blocking to achieve concurrency, messaging, loops, long enduring loops that stop the computation, stop the next statement to be executed. So, but well, let's start with the history. And in the beginning, there was absolutely no way to compose asynchronous I/O with CPU processing. Yes, we call execute a machine code I/O operation, but not long running I/O operation. For example, file I/O, because the system has to wait for the response. So early computers have only batch processing, and batch processing is pure processing. The input is all gathered at the beginning. There is a pure processing with this input, and the output was the exit or the result of the computation, normally in a printer or a tape. So that's how a Haskell was defined at the beginning. Because it was pure, it couldn't manage I/O computation in the middle. So at the beginning, all early computers were pure and reactive, for some definition of reactive. But of course that was not much, did not match with reality. We need interaction. So Unix Unix or the Unix at the time of the Unix 60s, there were some revolution in the operating system, so that the operating system managed to compose I/O, long-running I/O with processing. So we can call a react operation like if any other procedure inside or in the middle of normal computations with CPU usage. So how they do it? Well, they stop the thread, stop the program really at the first. There were no threads. Then fill the buffer with doing the asynchronous operation, and then when at the same time the CPU executed other threads or other users, and the end continue the thread with the data returned to the next operation. So, and in modern languages which have green trees, this works the same way, but in this case this operation, this background operation, is done by the runtime of the language. Unix allows I/O with computing, so the end result was the console application. Before that, there was no possible there's no interaction with the program. So the problem is that console application and the runtimes of languages compose a single I/O operation and do it with the price of blocking. But the fact is that we have many different kinds of I/O operation. If we are blocked in I/O action, we will lose the other events from other sources. So what alternatives we have? We have basically two alternatives or a mix of both. Either using blocking I/O actions and multi-threading. So we need parallelism concurrency. At some time, the concurrency will need mutable state, or we need even loop with no blocking, not a single blocking I/O action, and using callbacks or loop event handlers to manage these the events that arrive to the event log. So the event handlers update a multiple state. So in both cases we have a multiple state in somewhere in the middle. Does preclude does not allow composability. That's the problem. To solve this, to half solve this problem, OOP was basically born for this purpose. The first language, Simula 1, was born to handle events, many events from different other objects in a simulation. And the other pioneer language, Smalltalk, also was very successful because it was capable to manage GUI application with mouse and everything. Why? Because OOP decompose the state machine, the big state machine, in small state machines, each one its own state. So this become more manageable because we have many small state machines that communicate between them. But the overall architecture is very similar to a printer circuit without serial bus. You say that each chip has a concrete signaling. You have to be very careful to looking at the manuals to know what pin can be connected to what pin, not to exceed the voltage specification, or otherwise they will not work. So we have to be very careful in the design of OOP programs. Continuations coming from functional languages was a solution for this problem, because if we have an event in we can invoke the continuation, but the classical formulation of continuation in classical functional languages has a hard wide syntax, too powerful. We can do whatever, but it's not very manageable, and it's not clear how to manage different sources of events in a composable way. So I return to monads. Of course, the continuation has a because continuation don't break the recipe. It's like chips with a serial bus. You said that there is no these pins are similar, are the same, so we don't have to care, don't have to read much documentation, don't have to be so much careful. Even the box has sockets that either the chip match or not. If it match, probably it will work. So we have at the same time more freedom and less freedom to do brown things. But how to do this in software? Of course, this is not a sad analogy, but it shows some of the similarities. How to manage a continuation in a better way? Let's look at monads. a monad use a basic operator which is bind. Bind is concatenate two or more statements. Let's call closure what has been executed until a point, and continuation, the rest to be executed. Let's look with more detail. A monad's instance or a monad in Haskell is like something. The bind operator is defined with something like this. This is the bind in Haskell. G is the closure and F the continuation. Whatever we are talking about, the first operand is what has been executed until now, and this is the rest. So let's see this concatenation, which is the same than this, but in Haskell. Sugaring the expression is something like this. A is executed and generates an output which is passed to B, which generates output which is passed to C, which generates output that is passed to D. Well, so G at this point is this: A composed code with B already executed. So it is this Bx, and F is the rest, this one, which is set CD. So if we have start from a state monad, if we build the new monad, the transient monad over A with a transformer over a state monad, I cannot explain what is in detail what's a state monad, but think of like it can store things that can be retrieved later. So if we store these two things, we can execute them when something happens here. So let's look at a thing more concrete. Imagine this pretend to be a statement with waits for a blocking IO operation to return something, and when this returns something, it generates a thread which return a message or whatever the blocking IO operation did, and the continuation is executed to process the message. So how white events can be defined? It doesn't block, but it has a parameter of with a potentially blocking IO operation. So let's look at this. Here is the blocking IO operation. First, we look at a buffer. If it fails, this is pseudocode. Don't take it for the tape safe. It is just Haskell pseudocode. If the buffer is failed, it returns the buffer. But first, let's look at the condition when it's not already filled. If not, we execute a new thread. In a new thread, do the rest. So this white event doesn't block because the initial thread return empty gel the thread for alternative operations that may be next. So other maybe other wait events for another blocking IO operation can be run in parallel. We will see it later. So if this new thread is the one that block, and when it succeeds, it store in the buffer the message, and then execute the continuation, the closure and the continuation in a new thread, and immediately the white events execute again, executing another time the blocking IO operation. But let's look at this second thread. This second thread execute again the closure and the continuation. So, but the closure this is again white events. But this time white events find the buffer field, so it returns the buffer. So the next executing is the continuation, which is this. So we have threads continually being produced by white events, and they all are processed by the message, by the continuation. So we managed to make a blocking IO operation, not to block using different threads, but at the same time we have composability. Let's look at it. We have defined the alternative operation as a normal, very normal, set for some extensions for distributed computing, alternative instance. Because white events return empty in the current thread, it immediately execute all the asynchronous operations in which are asynchronous. So these waiting for events are running at the same time. Each one is spawning its own threads, and all of them execute the continuation. Keep is also a primitive of transient which keep the threads running because transient is inherently multi-thread, and the threads return empty very often. That will finish the keep loop. So keep the loop. So we use keep to run it. So we have that trans.io, which is the monad that runs this do operation, might return 0, 1, or n results, because you see here, how many results return this expression. We don't know, depend on the result of this and this. If this block infinitely, no result is returned, and so on. There are different versions of the same concept of white events. White events waits ever for repeatedly executing the blocking IO operation. Whatever it returns is returned to the transient operation within a different thread. Most of the time, we say later that we can control the threading. Parallel is the most general version in which the IO operation tell the parallel when to stop. If it return S down or last value, in parallel with the thread waiting in parallel will finish. Execute a single time the IO operation, so it ever return 0 or 1 result. and sample execute the IO operation each certain time. It pulls the IO operation and it returns only when the value change. So the polling is internal, and the trans IO operation, that continuation, it gets executed when the value change. Another problem, this is concerning parallel, non-blocking, composable handling of events. What about frameworks that set event handlers? How we can get rid of that inversion of control, this virtual state machine that the frameworks impose to us? Well, we can de-invert the event handlers. We can include the event setters in our recipe without breaking composability. And the trick is very close to the one used in wait events. Imagine that we have this handler that a framework gave to us, and the handler is the set handler is a program that get our event handler, and return IO normally. So we need this a kind of React that get the event handler setter defined in the framework, and we receive here the event, so we can put the we can continue the execution of the recipe. So well, how we can define React? IOV don't care about this because it's sometimes the event handler doesn't return IO, it returns another thing, so we use IOV, which is the second parameter. So what we do, we get the state of the trans IO computation. If the buffer of the computation is the buffer, or the event contained in the kernel is not filled, is this equivalent to the buffer. If there is nothing, we set the handler. That means that we are at the time of setting the handlers, because the application has never passed through React before. So we set the handler for the framework with the continuation, the current continuation of our recipe. And we pass, well, this is a detail because I copied the real code, that is not worth to detail very much, because we don't have time. But we pass the value of the event in the state, and return to the handlers, to the set handler, a value which now may be returned. The task that depend from this, and return nothing. So after setting the event handler, we let other alternative operation to be executed. And as before, when we run this, this is the real code, not the pseudocode of the previous sample of wait events. When we execute the continuation with this field, we execute again React, because it's the closure. This continuation is the closure and the continuation. The closure is React. React finds something in the event box and execute the continuation. Well, it's executed here, so it doesn't, since because it doesn't restart nothing. The continuation continues with the rest of the sentences that are here, and before it clears the buffer, the event box. This is an IRC client made with Transient. These are the only sentences that are from Transient. This is, of course, a standard alternative operator. This is really a little bit more long because it uses some new type definition, but roughly speaking is the same. We have in both cases for the input and for the output the same process in call, which does this thing. It wait from the input and write on the output. In the first case the input is the socket and print the result in the standard output. In the second case is the standard input and print in the socket. So we have a two-way composable IRC client, which you can compose with anything else. If you like, we can add here more operators, more alternative computations, both here or here, continuing the monad. So what we have until now is alternative computation that can be composed using the alternative operator. But what about concurrency? Concurrency can be achieved with monoids or applicative. So when we use async, that as you know is it wait for a single result from the IO operation and compose with applicative. The result of both IO operation are printed in the continuation. Sorry. And if we need some freedom to compose, some more freedom to compose, we can use applicative. So in this case, we can generate a tuple with two operands in the same way. This time generating this. You know that you see that both operations wait one for the other until both are available and then execute the continuation. So there is concurrency here, but it's composable concurrency because we can add more operands here or even alternative operators here, so we can have whatever expression of parallelism and concurrency here. So we have parallelism associated with alternative operator, concurrency associated with these operators, applicative operations, and monoidal operator. We have recipes with sequencing with bind. It's not an imperative bind because as we know, we will see we can go back, we can go forward, of course, and we can execute in the middle when an event happens in the middle of the computation, for example, when there is a wait event. So this is like a recipe. It's so flexible that it's indeed a recipe. We will see more on that later. Console input, because Transient is a general purpose library, we need to manage console input output, no matter if we have many threads. So and doing it composable way, in a composable way, with no blocking and things like that. It's possible, yes. We can do it with this using white events. Option is has two operands. One is the prompt, and is a value expected by the input. What we do is wait for events from a loop which read from a buffer. This buffer is filled by a special thread that is the only one that really reads the standard input and fill the buffer whenever the user presses enter. Each thread waiting for an option examine with STM the buffer, and when it matches, then the return the value, and the wait events generate a thread, and the continuation is executed. So because it's white events, we can compose in nice ways using alternative operator, for example. So this piece of code is possible. When we execute it, we see that the prompt, well, what it prints is more than the text. It prints something more informative, like this. Because options use white events, and white events return empty to the current computation, this is not executed, and the alternative operation is executed, which is this, which print the second message. And since because it returns empty, this is not executed too. But what happens when I press A? A is get by the by option, which execute white events really is waiting for here in a loop, and when because A is equal A, then return the B, and then in another thread, and execute the continuation, which is word. Sorry, hello, because it's A. In the same way, we can pass the inputs in the command line, so we can do this. This is the option used to notify the program that there is input next. So if we pass this separated by ampersand, the previous program will print word hello. Why? Because the first entry is B, and we know that options are executing in parallel in the two different threads. So no matter the order, what is comes first will be print first, and the second will be second. So the order, this is what it prints. To have more free input rather than fixed options, we can use this input, validate the input, print a prompt. If it doesn't validate it, another input and in another thread will get it. or nothing, or nothing at all. Anyway, this permit to enter strings to the to any thread. If more than one input get matches, the first will get the value, but because input does not use white events, it uses async. It only has one opportunity to get the value, so it doesn't get like option, which is active all the time. So we have seen that we can generate a lot of explosion of threads, and we need to control it because we can create composition with fault, which might generate as many threads as entries in a list. Using this, we call a scene, which return each one of these of the elements of the list using map, and we compose them using this alternative operator. So we are generating a lot of threads, each one for one value, but this is a waste of resources from the runtime, because there is a limit and probably will not run as fast as a single thread for some lightweight things. So we can control it using threads. In fact, the white events and the simple definition we saw before is more complicated, because instead of for, it inspects if there is threads available. If not, it waits for one thread available, etc. So the net result is that we can execute whatever transit or computation with a limited number of threads, even with zero threads, because this is zero means that to run with the original thread, no new threads is executed. And in this case, this is with this definition of choose and this continuation, this is a loop, a normal loop. And by the way, we saw in the IRC client that we use threads 1. That is because if we don't reduce or control the thread to 1, it might be that messages arriving here can mix together, because white events will read from the socket very fast and might clutter the standard output. So this is a way to assure that all the socket input comes in a ordered way, because we have one only thread. Another useful thread control primitive is one thread. The usefulness of this is as follows. We can generate a big number of threads. Even if we have here thread 1, here imagine each time that we select an option, it generates a new thread here. So we may be here with a lot of threads running that are not interesting, because maybe these options are or this run interpretation can span other options that are waiting too for input. So each time option here is selected, another option will be running with the same option, we expecting the same value, so we don't need that. So to clear this, we use a one thread. One thread, what this does is assure that the continuation is ever one single thread. It kills everything else that is running when one new option is successful. So another is kill childs. One thread really use kill childs to kill all the child of these and these options. So it's a little more than kill childs before executing the continuation. Well, there is more subtleties here, but don't want to be hooked on that. State must be pure to be composable. And to be high level from the beginning, we need to store whatever user defined data. Set data or set state is the primitive for storing state in the state monad of Trans.io. The way to do it is sorry is to use set data. Whatever you define can be stored in the state. Get S data return the state of this type. If there is nothing, it stops. It return empty. So to assure that there is ever a default value, we can use this. And because it's pure and the state is inherited by the children, the children threads, we can have things like this. Imagine we set the data of string values to hello, and then there is a generation of threads here using white events for whatever output is here. All the child threads executed inherit this hello state, and even if we set the data after with word, this doesn't change the state of all the previous statements. That is because the state is pure. Let's say that the state progress downwards, but not backwards. That behavior is normal in a state monad. The difference is that we have whatever state kind type as long as it is typable. Evars are the way to communicate two alternative branches of the computation which has nothing in relationship, no apparent relationship. We might need to communicate events between different branches. It's easy to communicate the event to the continuation, to my continuation, but when we have to communicate non-locally, I have to use something like evars. Evars are simply wait events watching for a channel. The channel. A channel is one-to-n. So if we have many evars reading reading the same sentence, all of them will receive each value. So if we have is this new bar, simply create the channel. If we have two alternative computation reading the EVAR and one third updating the EVAR with empty at the end, so this computation will never return anything to the continuation. If we write 10 times to the EVAR, both EVARs will reading EVARs will be activated, will return one thread for each value, and we will those 10 threads or 20 threads, because there's 2 times, will execute this. So we saw something like this, not really in the same order, because each thread will run at its own pace, but we will see each entry duplicated. Mailboxes are well-known evals which are in the state of each node, so we can get the eval and update, write and read it with a special interface, which is a mailbox. But in really they are evals. And here come sections where we can see the virtuality of the recipe metaphor. Exceptions do not compose because one exception can do whatever, and one exception point may not know what to undo, what resource to free, what to do in a computation, unless you know all that has been done doing the computation until now. So it breaks every rule of maintainability and black box isolation. So moreover, we are not here talking about many threads, multi-threading, which works very badly with exception. A better alternative is backtracking. We'll see this example first, and for the proposed primitives, and we'll see how they can be defined using continuation, etc. Let's look at this example. We have in an online shop, for example, book shop, the user select a book, and then when it introduces the card, the book is reserved for during the operation. He pays the book and the order is processed. If there is an error in the payment, we need to unreserve the book and do whatever things has been done before, with the perspective of the book being sold. So imagine that there is a undo handler that in case of backtracking, in case of failure, demand another card to the user, and in case of being successful, it continues forward. And forward should execute from this point on, again reserving again the book, paying the book, and again the same thing, the same navigation. If the user doesn't manage to introduce the card, forward is not executed, and execute back again until every action has been done. Well, how we can define an undo? An undo is first inspect the backtracking flag. If there is no backtracking, it set up his own handler and the continuation in an undo stack, which is a special state that is managed by the monad, but like any other user-defined state. And after registration, execute the action. And if backtracking is active, it executes the handler. Undo, which initiate the backtracking, check the backtracking, get all the list of backtracking actions, and execute each handler. After executing the handler, inspect it backtracking hold still. If there is backtracking is still active, then proceed with the next handler in the stack, and so on. If the backtracking has been overcome by forward, then execute his own continuation, which in this case is from this on, where it executes the closure and the continuation. So we have it. To inform the undo operation about what was the nature of the failure, there is a special primitive called unfinished, which in reality undo and unfinished are particular cases of a primitive called back. Unfinished has either a normal termination or a exception as parameter. So unfinished is unlike undo. On undo can inspect the nature of the error, of the relation of the error, and can do corrective actions, or it can do nothing, or can continue backtracking. In this case, it used to restart a node when the remote execution has not run well. So imagine we run this. The runat internally has invoked backtracking. It will invoke finish. Then, well, finish is a particular case of undo. And because it backtracks, execute on finish, and this restart the node and execute the continuation, so redrat is executed again. Well, it needs a number of tries and so on, but you see the logic. Another important thing of transient is logging and replying. This is useful for checkpointing the state and continuing the execution when something fails, or we need to stop the computation and continue later, or we can execute in another node something initiated in a local node. So it's also useful for debugging. So logging in transient is quite different from other kinds of logging utilities. because what is logged is the result of a computation of the parameter. We define a log state, which either store dynamic values or signals that tell the computation that the operation is being executed or is waiting for a synchronous operation to finish. Let's see how logit, which is the basic operation, works. Logit applied to a parameter. In this case, we set the log to a value. Suppose that this value is the same type that foo uses. Logit because C and the state data something, what it does is get this something from the log and doesn't execute foo. So what print x is the logit thing. If we don't have this, what logit do is to execute foo and put it in the log using a sentence similar like this. So at the end, we have the state filled with the log of this execution. How logit is defined? First read the state or the logging state. If not, if initialized to something void. Replay is used to signal the computation that it must reply from the log. If this is true, the log is read. So it reads the first result and matches to the kinds of data expected from F. If not, is something, if there is nothing in the log or there is no replay, it executes F, but first it informs the log that something is being executed or waiting for. Depends. This is pseudocode, as always. Don't take this as the word code of the logit. This is simple pseudocode with more salient things of the code. And when F finish, we update this entry with this symbol with the real result. The next thing is that because logit doesn't change return the same time F, we can have cascading execution of logit, because F may have another logit sentence, and the sentence can call another. This computation, what I mean that this computation can generate a long log and can be very complicated. But at the end, all this log generated BF is discarded, and only the result is put in the log. So that's a good property, because the log doesn't grow very much. Only the top level results are stored. And there is another good properties of this, because this will work well with alternative computation and so on, so it's consistent. Logging is useful where there are primitives for recovering state and checkpointing state after files and so on. remote execution is the main usage of logging. Let's look at this simple example. This first, as always, I use the primitive before defining them to make you to let you make an intuition of what we intend to do. First, we have something like listen, warhol, and teleport. Local is like logged, is logged but with type safety to make sure that all which use remote invocation call logged. But look at this. We have listen, which listen for messages from a socket, and this is an alternative computation that return immediately. So the continuation is executed in both nodes, locally and remote node that are running. Both wait for option X to be entered by the user. Imagine that this local computer is we enter S. We can enter here also here because and the operation will be in the same but in a reverted way. That if we press S, local record the S. Local execute a full operation with return and earth that are also logged by local, and then we have warhol which connect to the remote node, which is this, and then we have teleport. Teleport shall send the log to listen in the remote node which is waiting for the socket. Listen shall establish our the log received as active using the flag true in the state data. So local will notify that there is local is executed because listens has return something from, and the thread generated from this branch by white events execute local, which gets the option from the log because it was logged here. Then execute the second local, which get the air from the log. Then execute warhol, which does nothing, must do nothing in the remote node. Teleport must do nothing in the remote node, and execute this because there is no longer more entries in the log. So this is really executed, and what this does is to print the error that we generated in the local node. That's the way we execute. We continue in a remote node what we started in the local node. What we see what local and listen do. Warhol simply connect to the or use a connection with the node that we intend to connect and set the connection data. All of this only when we are in the local node. If in the remote node we do nothing. Teleport does something similar with the recovery state. If there is no recovery, we are in the master node, in the node that is executing the computation first. Then we get the connection data and send through the connection the log. That's all. Or that's the initial definition of teleport. Now it's more optimized. Or if not, we do nothing. That's all. because we can have not very much long logs, because we only log the top level calls, but we can optimize the replying by reusing closures. Look at this. We have the same listen and return, the same warhol, the same option, and x, some x is generated here, which is logged. Later we will see that there is 10 threads generated here, but let's look at 1x. 10 teleport, transport to listen. The warhol does nothing, option get from the log, and we read this first value, print the value, because we don't have more log, this is executed. Then we calculate a t with the value +2, and we do a teleport back. This teleport, which return to the original node, instead of sending everything again to initiate from the listen, what send is only this new, what is new in the but the original node don't know, which is this, and send the identifier of this continuation. And what listen do is let read the identifier of the continuation and the log, and invoke this continuation directly instead of executing this. And because execute the continuation, because trans.io permitted to manage continuation, it replay this section of being logged from the remote node, and this execute this new code, calculate another seed, send another teleport, which use this identifier of teleport or continuation with the remote listen, read and execute with this log, and finally execute, print the last set calculated in the previous node, in the local node. so we have reusing of closures, and we have that is faster, of course, but in many situations, but also we can access our own variables here in the computation, because the closure are respected. So we can define, for example, a eval, and we can write the eval here and things like that. But if we listen from the beginning and re-execute every log, this sharing of variables will not be possible, especially variables that are not serializable. Know that this choose generate 10 threads, and the 10 threads generate x, and the report send 10 logs here, and teleport back, send 10 logs here, and this generates send generate and send 10 logs here. So there will be streaming here with multi-threading. So you can say that Trans.io computation, transient computation, have handled naturally remote streaming, in both directions. In this case, the local node initiates the streaming, but we can initiate it in the remote node. Look at this. There is a wormhole. Immediately we teleport, and there is a remote computation that generate events from foo, and all these events are transported by teleport to my node, to my original node, and send that execute the wormhole. So there is a streaming back from the remote node to my local node. We can also move to a third node or fourth node using cascading wormholes. So we move to a node 1, and we connect to a node 2 to move to the node 2, etc. This is a ping pong program using wormhole and teleport. What we do is teleport and print the message, teleport prints the other message, so each time the one another node print ping and pong, because it is in a loop using a communication open by wormhole. We can create high-level primitives with wormhole and teleport. For example, Ronat use a wormhole and 2 teleports to execute something in the remote node and return the result back. For example, imagine that the other node has a database, and we has this database and return the result back. This is the arrangement. 2 teleports. In the middle there is the process that is executed remotely, and because there is a second teleport, the result returns to the original node. We have 2 new things. One is logged-C, which is in reality cascading logging, so that we log the result and forget the intermediate results here. So this is a kind of optimization. And set slave logged-C is the same as logged, but in the cloud monad. And because logged can be in cascade, that's the net effect is that the log is shorter. Set slave is here because teleport switch the master role to the remote node. We need to execute proc in master mode because proc may have many alternative computations. What set slave do is to signal alternative operator, not to compute alternative operators, because if we don't have this, the remote node will think that is the master node and execute everything, every alternative computation that it finds. With set slave, which is not really this statement, this is pseudocode. In reality, the changing of state variable. With this, the remote node has a slave when the procedure is executed. While it's executing the procedure, it executes that master. This operator tell transient that it doesn't matter if proc, retard, or stop, this has to be executed. This is the meaning of this operator. This can stop, but this must be executed, because if not, alternative operators in the remote node can be executed. We don't need that. So this operator is assured that this is done. We can do whatever combination that we use for concurrent and parallel programming. For example, running two things in different nodes and get the result and summing the results using applicative. Or we can do execute in parallel two computations. Both will return a different result in a different thread, and in this case use collect to get the first result. Collect is another primitive that does exactly that. This is useful for basic resilience. We can execute the same in two nodes and get the first. We can, of course, sequence in remote actions. So we have the same algebra and same kind of recipe management that we had in the case of parallelism and concurrency, but this time with distributed computing. We can do also asynchronous communication between different nodes and different branches using EVARs or mailboxes. What we do is use RANAT to translate the computation to the remote node and write his remote mailbox or EVAR data. We can, because this return unit, after this we know that the remote node has received the value. If we don't want this, we can add empty here to avoid the response back, because RANAT will ever return unless there is an empty here. In this case, teleport is not executed. That's interesting, because we can, even if using RANAT, which has to teleport, we can send one-way messages with no response. So the actor model, we can do it with transient using mailboxes. We have also cluster-oriented operation. I mean, cluster the operation with many nodes at the same time. To get the list of node, we can use connect, and this is the way to use it. When we connect with a remote node, we interchange the list of nodes between two nodes. Suppose that I have alone and I connect a network of nodes already connected. When I connect to this remote node that is connected to in a network, I receive the list of all the nodes on this network, so I can do things with this list. Also, if I have a network and the other node is connected to another different network, when I connect both nodes, there is an interchange of nodes, so that both networks get connected because it notify my connected nodes, my already connected nodes, that new nodes are available. So there is a kind of synchronization between both networks connected now. So finally, all the nodes have all the nodes available in both networks. hopefully. So what we can do with those list of networks, we can do this like things like this. Cluster is a primitive which is use a process that is executed in all the nodes, and each node result is returned in a different thread to the original node that initiate the call. So we have if we have n nodes, we have n responses in n different threads, unless we use thread limits. So like in the case of wait events, so we can control the threading also in distributed computing. Initialization of cloud application, because we have console input and command line input, we can use that to input cloud parameters. For example, this is a typical initialization. We have keep prime is keep without console input, but anyway it can get the command line input, and the command line input is in this case read by disk, which is init node and input nodes. Init node read this segment and input nodes read this segment. So init node initiate the listen with the node entered by this string, this segment. It does something in for web application, but this is later. After it's initialized, input node read this because it's next in the input. So what input nodes read this? Add this means that connect to this node, or better say, add this node to the node list. What tell if this has to be connected or not is with this flag. If this is yes, it connects really. So both nodes interchange the node list. So this is the way to create, to initiate and connect different nodes in Transient. We can have many nodes at first, or we can opt to connect them. There is some example that we can see later. That no, we will show it later. Services. Until now, we connect identical programs or programs that are very close. It's not necessary to be identical programs to communicate to transient programs, because we use logs. So we log values, so there is some freedom. In fact, we can connect, we can invoke in the server a closure in the browser, which is quite different code compiled with different compiler. And even we can communicate programs in different languages too with this solution. But anyway, services free us from any kind of dependency in, in the program definition in both sides. We both programs are completely different, and still we interact interactively. Um, Imagine that the database is a remote program initiated by a service, and we call it with some parameters because services don't share variable scopes. We have to pass them explicitly. Uh, but anyway, imagine that this read new register from user interface or whatever and pass it to the database. Well, the database in the same call can return back any update of this kind of register if we like. So it can respond reactively to the to whenever another node update the database. So we can have this kind of reactivity even if we don't have identical programs. This is similar some kind of reactivities down here, but so because we send and we receive, or here where the remote node send back results, or mix it of both. We can have a choose here and a choose here, so we return, we receive more result than we send. But in this case, the both programs have no sharing of code. This service can be a database or whatever that we need to. So we can split the application, the distributed application in different services without having to manage code in its node that doesn't make sense, because one node can be devoted to database, another to user interface, and etc. etc. So that's the good thing about services. We have some kind of easy primitives to manage services, which make them easy to initiate and program and invoke. The services is defined by a repository and an executable, a name of the executable. So we identify the really a program in the internet. And run service is initiate the service. No, sorry, it gets the code of a service and make it available to other nodes. It has the listen to listen for request for this service. Call service is the one that call a remote service and call it with the simply the Git repo and the executable name directly, and the parameters are the one passed to the call, and the result is a one or many or zero result. Call service is a specialization which send a node that we know that hold these services with the same parameters and return the same result. So there is something between this and this that intermediate between them, which is the monitor service. The monitor service is a special service that maintain other services, even execute them and even install them. Is executed like this. Run service establish that this service is being available to the network, and it receives as parameter in each invocation a service name. What the service does first is to find in its list of nodes for this service. It looks for this service in the list of already executed services. If not, it try to run in this node. If not, it try to run in other service of other nodes, other nodes that might be willing to accept this service. Why run here might not succeed, because there is a checking of permissions, and the checking of service depends on a temporal personal information number sent by the call for the service call. So if this is successful, the service is installed. If there is it not installed, it is run and return now. Of course, if the node is already running, is in the list of nodes, so everything. And run there use runat to call other services in other nodes, because the run service run in a welcome node port, which is 3000 at this moment. So we can ask this monitor of further nodes knowing only the host names. So this is an example. The call service, which is here, ever invoke the monitor service first, because it doesn't know the node, the real node. It asks to the monitor first find in log for it in is local num list of nodes. If not, it call the monitor service with this ping and the service. In reality, there is a ping here also as parameter. So the monitor service will find it, or will install and run it, and because it returns the node, this node will be called service prime to invoke the service, to really invoke the service. This we have here a failure. On failure, when if the monitor service is not executed, or is down, the very call service start the monitor again and retry it. MapReduce is another application of wormhole and teleport. This is one console example which get the free text input, and with input, and calculate the the number of occurrences of words using all the nodes available. The implementation of MapReduce use the same used in Spark, the basic architecture, Spark architecture, in which the input is split if it is already split. What map is to apply the operation locally to the chunk which is in its local node. Then it because each word is missed in each word it may be in each of the nodes. We send each word to a single node. For example, hello goes to the same node, so that all the words hello occurrences are combined in the same node. So we have to do something like what's the name of a translation of data from each mapping node to the resulting node, which will some other result. Shuffle is the name, like a card shuffle. So at the end, all the results are summed up, and the results are presented. There is a complex choreography here, and it is a proof of how well the composability of transient works, because if you expect reduce is made of parallel and concurrent operators. And web, unlike the Spark implementation with use of object-oriented computing, and is very, very complex. Transient also execute web application. To do that, we started like in any other transient distributed application. It will have any node, and we can also have distributed web application too, with many servers using add nodes, so server node can connect. But let's look at this. The great thing is that a transient application can run both browser programs and server programs at the same time. On browser, is a filter that only allow this to run in the browser, and on server only allow this to run in the server. If the on browser and on server is not, especially on browser, there is not a problem, because this browser program, when executing in the server, will stop, because every rendering operation in the server is defined as empty. So it doesn't matter if this is or not, but for a sake of illustration, we use both. This is useful too, because we have to avoid the browser to do server operations, for example. How we run in both browser and server, we have to compile the program with this, using no place to store the result, and we compile normally the program, and as always we start the program with this in the command line or in the program input if you like. How it works? It works because this time, which is running in a node, as you see, also wait for HTTP request. And when an HTTP request arrives, it sends all the code generated by GACIS. And what does in the browser is execute this exactly same code. So what it does is execute init node, which in the browser send a WebSocket, send a wormhole to the server opening a WebSocket. So this browser program will be executed within a wormhole with the server. This you can look at how on browser is defined. So because we run browser program with an wormhole with a WebSocket opened to the server, we can, well, on browser is again here, it's not necessary. We can do things like this. First, imagine we have a widget that demand a string, which is whenever the user press the key or release the key, the input is sent, is logged, and is sent by our remote to their server. You see, this alt remote is this one, and teleport, the call to the remote execution, one teleport back, and return whatever the remote operation in the server return. So that is because we have a wormhole already open. So with the proc operation is this in the server, which print the name and return this hello name. So we have this back in this browser and render what the server has returned. Of course, we can have a streaming from both directions, in one direction or another, and we have all the freedom of remote computations. And this is the end of the demo. Well, the presentation, the demo will be in another video. Thank you very much. For more information, you can look at the repository of Transient, which is in the, well, it's not here, it's a failure, but anyway, thank you very much.